Okay, so last time we started this numerical, and this numerical was related to external flow over the sphere. Okay, so this is actually something which you saw there in the CACs, but actually you go through in an overview, and if you remember, or if you can see in the videos that you made there, so the ink was placed or printed on the photovoltaic panel, okay, and that is a conducting ink. That is that ink which is going to generate or produce the electric circuit, okay. So that's the conducted ink, and what they used to do is there was an ink jet, and the ink jet throw the ink in the form of droplets, and that fell on the surface of the photovoltaic, okay, and so it is printed, okay. So the internal electrical circuit is printed with that inkjet printer on the photovoltaic panels, okay. So this example is basically about that case. So normally when the ink leaves the inkjet printer as a droplet, it is at around 200 degrees centigrade. It is at around 200 degrees centigrade, and it's already at the terminal velocity. Now I explained it to you in the last lecture what is terminal velocity. So what is terminal velocity?
Free falling object.
Yeah, free falling object, but it's the maximum possible velocity. After that, velocity will not increase further. So if something is already at a terminal velocity, will its velocity increase?
No.
If the velocity is not increasing, what is acceleration? Zero. So the effect of gravity is not acting when the body is actually moving at the terminal velocity. Effect of gravity is the acceleration. If there is acceleration, then velocity should increase, but the velocity is not increasing. That means the acceleration g is there, but it is cancelled by the other forces, buoyancy force and the drag force, okay. So the velocity is constant, okay. Now the thing is that when the droplet leaves the printer, when the droplet leaves the inkjet, it is at around 200 degrees centigrade. The better thing is that when it falls on the photovoltaic panel, its temperature should be around 50 degrees centigrade, okay. There is air around, so the droplet is falling, and as the droplet is falling, it is passing through the air, so there will be convection coefficient, and the heat will be transferred out of the droplet to the outside air, right. And we want that once it falls on the photovoltaic panel, the temperature should be around 50 degrees centigrade. So in this question it is asked that what should be the distance, of this panel with the inkjet, with the point where the droplet is coming from. You get it? So larger the distance, smaller will be the temperature at the time when it dropped the panel. Larger will be the heat transfer that will take place. Smaller the distance, larger will be the temperature at which it falls on the panel. Do you understand this concept or not?
The temperature or the heat transfer?
Temperature, okay. So what we want is that we want enough heat transfer so that the temperature becomes 50 degree when it falls on the panel, okay. So what we want to know is what should be the length, what should be the distance for when the photovoltaic panel should be placed above the inkjet, what should be the distance between them, so that at the time when it falls on the photovoltaic panel, when the droplet falls on the photovoltaic panel, its temperature is around 50 degrees centigrade. Do you understand the problem statement or not?
Yes.
Okay, so now let's read the problem statement once again so that we focus on it. Electric circuitry is written onto a photovoltaic panel by depositing a stream of small diameter given. Okay. By depositing a stream of a small diameter given 55 micrometer droplets of electrically conducting ink from a thermal inkjet printer. The drops are at an initial temperature 200 degrees centigrade, right? And it is desirable for them to strike the panel at a temperature of 550 degree centigrade. Okay. The quiescent air, what is quiescent air? Stationary air. Okay. The quiescent air and surroundings are at T surrounding equals to T infinity equals to 25 degrees centigrade. And the drops are ejected from the print head at their terminal velocity. So the velocity of the droplets is basically the terminal velocity. Okay. Determine the required standoff distance. How much is the standoff distance? How much is the length between the panel and the thermal inkjet printer?
Photovoltaic and the
Yeah. So from the point where the droplet falls, what should be the distance between that point to the panel itself? Okay. So determine the required standoff distance between the printer and the photovoltaic panel. The properties of the electrically conducting ink drop are rho d given, CD given, and K given. So density given, specific heat given, and thermal conductivity given for the ink.
So the droplet leaves the inkjet with a 200 degree temperature,
Yes.
and it must be at 50 degrees Celsius.
At the time when it falls on the
Also
photovoltaic,
the panel.
when it falls on the photovoltaic panel, exactly.
So we need to calculate the
What should be the distance?
distance.
So do you understand the problem statement? Okay. Now tell me, what is the relationship between distance, velocity, and time if acceleration is 0? Dynamics. If acceleration is 0, what's the relationship between distance, velocity, and time? Velocity is equals to distance over time. If the acceleration is 0, right? In this case, it is at the terminal velocity. So the effect of acceleration is not actually affecting the body, right? So for our sphere, we need to know distance is equals to velocity upon time. If we know velocity, if we know time, we will find this distance, right? This is the problem. That's the problem. So let's talk about the velocity. Velocity will be what? It will be the terminal velocity. But is it given what is the terminal velocity? It's not given. However, we can find it. And this is actually what we did last time. Okay? So, yes, by doing the force balance, okay? So we have the force of gravity acting on the droplet, F is equals to ma. Okay, but mass converted in terms of density and volume. So that's the density and this is the volume. So this force is equals to two forces. Force of buoyancy and force of drag. Force of buoyancy is basically what? It is the weight of the air displaced. Weight of the air displaced. So weight of the air is again mg. But this time m will be for the air. Okay, so it will be rho into volume. Volume will be the same, but rho will be for air.
Volume of what, doctor?
Volume of the sphere. So this is your sphere. This is your droplet, which is falling. Okay, so this is falling, and it is passing through the air. Is it clear? And plus force of the drag. So drag force is what? CD into frontal area. This is the frontal area, which will be area of the circle, okay? Multiply by rho v square upon 2. Remember this formula? This comes from
Coefficient of drag.
coefficient of drag. We had that.
So we have two forces are acting upwards.
So coefficient of drag is equals to, okay. Yes, two forces acting upward, one force acting downward, and at the terminal velocity, they all cancels each other. Okay. So now in this equation, everything is known except the velocity. So if we simplify this equation, it will become this. You can simplify it. Okay. And then you can find the terminal velocity. So terminal velocity is find out, and it is find out to be 190 millimeter per second.
Do we have time?
So right now what we have the velocity. We have found out the velocity. Is it clear?
Yes.
So I'm going to hold here, ask you, do you understand how we found the velocity?
Yes, but why in millimeter per second?
Oh, it's okay, don't write in millimeter per second. Keep it in meter per second, it's fine.
Can you write the equation of the equilibrium force?
Yeah, I wrote this last
Rho and G.
before. So it was basically force of gravity on the droplet is equals to force of buoyancy plus force of drag. So it's mg, but this is for the droplet. So mg, but this is for the air, plus cd frontal area rho, so rho v square upon 2. Fine. So we got this velocity. Anybody has any issue in finding the velocity? Now if we know the time, we can find out what is the length. Okay, what should be this distance? Now how to find time? So this is actually now becomes a question of chapter number 5. This is a transient convection, right? This is the sphere, this droplet is a sphere, and its temperature initial is 200. The final temperature we want is 50 degree, and we want to know that how much time will it take until it reaches that temperature. So do you remember this formula, this formulation? So theta I, or I can write here as theta I upon theta is equals to exponential HAS time upon rho V, rho VC. Okay. And there was a negative sign, I hope. No, in this case it is not. So do you remember this thing? It was in chapter number 5. So here this is now become a transient problem. This is a transient problem that you have a droplet, it has initial temperature, and you want to find at how much time will it take until it reaches to the final temperature, and it is losing heat, right? So now if you use this formulation, you will be able to find out the time which is required for the temperature of the droplet to drop from 200 to 50 degrees centigrade. And once you know the time, you can find out the length. So now if you see here in this equation, so theta I is what? Theta I is Ti minus T infinity. Ti is T initial. So you know what is Ti. You know what is T infinity. Okay, so this thing is known, this thing is also known. Theta final. So it was theta upon theta. Theta means whatever the temperature you want to find. Okay, so this is theta final. So theta final will be T final minus T infinity. T final you know, and T infinity you also know. Okay, what about the other parameters? So the parameters are the rho of the droplet, the specific heat of the droplet. Okay, here it was V upon A. If you see here, V upon A. So V upon A, we know that for a sphere, it's R upon 3. It's radius upon 3. Or you can just substitute the values, you will get it. Okay, so V is what? It's 4 upon 3 pi R cube. A surface area is what? 4 pi R square. So substitute the values, you will get R by 3. In terms of the diameter, it will be D by 6. R by 3 is D by 6. Right?
What about the H, the coefficient?
Okay, so now we have, okay, so now we need H. So for H, we are going to use the formula from this chapter. So in this chapter, what we were studying the heat transfer, external flows across the bodies. So this is the sphere. So external flow across the sphere. Okay. So if you remember the formulas, so these were the formulas here. Okay. So we had the formula here by Whittaker. Okay. If we have the heat transfer across a sphere, but for a freely falling body, the special case is dealt by Rance and Marshalls, and the formula is this. Right? Since we know that this is a freely falling body, what is the difference between a freely falling body? So there is a possibility that I can produce some wind here, and then I put a sphere here, and so there will be heat transfer from it, but it is not a freely falling body. Freely falling body is whatever is happening because of its free fall effect. So for a freely falling body, this is the specific equation. Okay. If it is not a freely falling body, then you will go back to this general equation. Okay. So in this equation, now you will first find out the Reynolds number, the Prandtl number. Okay. Substitute the values, find out the Nusselt number. Once you know the Nusselt number, you can find out what is H. Once you know H, you will find out what is time. Once you know time, you will find out what is length.
Doctor, the relationship for length is not like this. This is like acceleration. V upon T.
L equal Vt, not V upon T.
Ah, you're right. You're right. So it's basically S is equals to Vt.
Yes. That's the acceleration V upon T.
V upon T is acceleration. Oh yeah, thank you. This is wrong. So S is equals to Vt, right? So velocity is equals to, so here in this case, so your S is basically your L. L is equals to Vt. So if you know V, if you know T, you write it. Thank you for correcting me. By mistakenly I wrote it. Yeah, this is Ghayat al-Fala who corrected me. So
The restart required.
you restart your restart.
Don't click anything.
No, it's recorded whatever you said. Okay, so so now we use this equation. It was the Rance and Marshall equation. Okay, and substitute all the values here. Okay, and before that we find out the Reynolds number. Reynolds number is Vd upon mu, because you need to get the Reynolds number. So velocity is the terminal velocity, diameter given, divided by mu, the properties of the air that we are going to use here. And use of Stokes law is appropriate. Okay, and then substitute all the values, you get the Nusselt number. Then substitute the Nusselt number, you get H. And once you know H, you substitute H, you will find out what is time. Substitute the time here, so L is equals to Vt, and you will get what should be the length. So even in reality there, they put it close to this, 5.6 millimeter or something. So even the distance between the plate and the inkjet printer, it's calculated. Everything is engineered. It's not just put the plate under, no. You have to see that what should be the distance.
In millimeter.
In millimeters. Okay. So is there anything in this problem which you do not understand in the question?
So this T is equal to rho V C D. This formula from formula
From chapter number 5.
from chapter number 5.
You remember this formula from chapter number 5? It will be in the book of formulas, obviously.
But we don't like in this way. T equals.
No, you will not have it in this way. You will have it in this way only. But then you make the shifting yourself.
Did we do it?
Yes.
In the video?
Yes, we do it. And you are going to do it in the homeworks as well. and you're going to do, and we did it in the class as well.
No.
Okay.
Just this number to also.
So when do you want to take your second exam? Because okay. So because right now I think you guys totally forget chapter number 5. So anything you want to ask regarding the solution of this problem?
It's fine.
Is clear? Okay.
So we finish chapter 7 or not?
No.
Doctor, did you have a clicker? Easier for you.
No. This is easy. This is easy.
The thing is the FG equals FB. We don't know it before.
You did not do this before?
No, يعني it is new for us.
It was supposed to be done. I don't know whether you did not do it. But anyways, now you do it. And in any case, you will do this in fluid mechanics. Fluid mechanics, when you are going to study the buoyancy and everything.
Don't rely on
This course is heavily linked with fluid. Anyways, now let's have another topic. This is a more realistic topic, and this is about the flow across a bank of tubes. Normally, it's not just a single tube that we have and the flow is across that. Normally, we have many tubes arranged, and when we have flow across those many tubes, then how to determine the heat transfer coefficient. Okay, how to do the calculation. This is about this. Flow across the bank of tubes. Focus on each and every word. Flow across. So the flow is across. Okay, so it's a cross flow. This is a legitimate terminology. Cross flow, parallel flow. This is a cross flow. Okay, so whenever you have the tubes and the flow is going across it like this. So this is a cross flow. So cross flow, whether in this direction, whether in this direction, in this direction, this is all cross flow. But if it is in this direction, this is not cross flow. Okay, so any direction which is any direction which is in the radial direction, flow is in the radial direction, that is cross flow. But in the axial direction, that's not the cross flow. So flow across the bank of tubes. So we have many tubes here. So normally what we do is that in the tubes we have a fluid flowing, and outside we have another fluid flowing in the cross direction. And obviously if there is temperature difference, so the heat will be transferred from one fluid to other fluid through the tubes. Is it clear? So now we have two different kind of arrangements for the bank of tubes. One arrangement is known as aligned. If the tubes are like this is aligned arrangement. The other tube arrangement is, this is the aligned one. Okay, the other is the staggered. Staggered arrangement is like this. So the tubes are not in, the tubes are not aligned, but they are displaced a little. Okay, so this is in between the two, and this is in between these two. So this is in between these two. This is in between these two. So each one is in between the previous row, two consecutive ones. Okay, so this is a staggered arrangement. This is the aligned arrangement. So we have two different arrangements. Do you understand these arrangements? Now we have two different distances. One is transverse pitch. Transverse pitch is ST, and ST is basically this distance. So if you have number of rows, row 1, row 2, row 3. So distance between the tubes within a row is transverse pitch.
They have to be equal.
They
have to be equal.
They have
to be equal.
Yeah, they should be equal. Okay. And then there is longitudinal pitch, SL. SL is distance between the rows. So this is SL. Transverse pitch is distance between the tubes in a row. Longitudinal pitch is distance between the rows. Is it clear? Similarly, here you will have in the staggered arrangement. So this is ST. This will be SL. Okay. And then we also have for the transverse arrangement, for the staggered arrangement, we also have another distance which is SD. SD is center to center distance between two tubes in different rows. Center to center distance. Okay. So in this case, SD and SL are same. In the aligned case, SL will be this thing, SD will also be this thing. But in this case, SL is this thing, but SD will be a little larger than SL. See? So that's one of the difference between the aligned arrangement and the staggered arrangement. Okay. So in the aligned arrangement, SL and SD are same, but in the staggered arrangement, SD is a little greater than SL. Is clear? Okay. Now, if we want to find out the heat transfer across the bank of tubes, then we use Zukaskas equation correlation. We studied Zukaskas before as well, but Zukaskas does not stop there. Okay, so Zukaskas does not stop there, and he also suggested another correlation, and this is for the bank of tubes. So this is also Zukaskas correlation, okay, but it is a different one. So this correlation is C1 Reynolds number power m max. So we need to get the maximum Reynolds number, okay, into Prandtl number power 0.36 into Prandtl number over Prandtl number s power 1/4. Whenever you have this kind of equation, so at what temperature you want to find the properties?
All of them on infinity, S, RS, and 7.
At the surface. So here will be the surface of the tube and the properties of the air free stream properties. So you will find all the properties at the free stream except for this Prandtl number PRS, which will be at the surface of the tubes, surface temperature of the tube. Okay.
But the pipes from the middle, are they different about the surrounding?
I couldn't understand your question.
Go back to the previous slide. The pipe on the middle,
Yes.
is it different than the others?
Oh, you are saying that does this pipe has a different temperature than the others? We are assuming that all have the same temperatures. We are assuming, but yeah, that's a genuine question. There is a possibility that there is a temperature gradient between pipe to pipe. Okay, so for those cases, we are not going to deal with those cases right now here.
Doctor, there is another option for the tube. For what this tube? Why like this?
There are two options. They have some advantages. They have some limitations. So why are we using these tubes? Just to transfer heat.
Like fins. What's another way?
Look, fin is a solid body which is transferring heat to outside. Here we are putting a number of pipes. So if we want to transfer heat from one fluid to another fluid, so that's a heat exchanger. If you want to transfer heat from one, suppose you want to transfer heat from water to air, but you don't want water and air to mix with each other. So what you're going to do? You're going to put one of the fluid in the tubes and another fluid outside it. Okay, automatically heat will transfer because the other fluid is in contact with the tube. Inside the tube you will have another fluid. Okay, and whenever you have the temperature difference, so heat will transfer.
There is a chapter about that exchanger.
Heat exchangers, yes. That is chapter number 11, I think. That's about the heat exchanger. So do you understand the concept here?
Yes.
Okay. So we got this formula, and now it has three conditions. The first condition is that NL be greater than 20. What is NL? NL is the number of tube rows. So you had one tube row, second tube row, third tube row. So this formula is applicable if the number of tube rows are greater than 20 or greater than or equal to 20. Second, the Prandtl number should be between 0.7 to 500. This is the range. And the Reynolds number should be between 10 to 2 into 10 to the power 6. So if your Reynolds number, Prandtl number, NL are between these ranges, then you can apply this formula directly. Is it clear? Where NL is the number of tube rows and all properties except PRS are evaluated at the arithmetic mean of the fluid inlet temperature, okay, and outlet temperature, and the constants of C1 and M are listed. Now the thing is that here, this is another important point. We need to get all the properties at the free stream temperature. Okay, so you have all these tubes and the flow is flowing across these tubes. So the temperature here will be T infinity, right?
Yes.
Free stream. But do you think that the free stream temperature would remain the same?
No.
No.
It will change. Okay, because the heat is being transferred, okay, to or from. So we will have a mean of these temperatures, say Ti at the inlet, and we will have a mean of these temperatures once it passes through these banks of tubes, so T out. Okay, so these properties are not found out at Ti, neither they are found out at TO, but they are found out at an average of Ti and TO.
So, do the pipes producing heat? The pipes, are they produce heat?
If there is a heated fluid inside, so they are producing heat. You get it? So if you have a pipe inside, say 300 degree centigrade water, so heat will come out of it, right? Is it clear? So they are not producing heat, they are just transferring heat from whatever the fluid you have inside. Depends upon what is the temperature of the fluid inside. Okay? So the properties here are not calculated at Ti, they are not calculated at T naught, they are calculated at an average of Ti and T naught. Okay? Because here in this case the free stream itself, its temperature is changing as it passes through the bank. Is it clear? So, and the constants C1 and M are listed in table 7.5. So you have a table which will give you the values of the constants C1 and M. Okay, and if the number of tube rows are less than 20, if the number of tube rows are less than 20, then it is said that you cannot use this formula. So what is the change here? So if the number of tubes are less than 20, then you use this formula, which is basically what? C2 into above formula. So instead of saying that, I can write here that ND is equals to C2 multiplied by C1 multiplied by all these things, where C2 will be 1 if the number of tube rows are greater than 20.
So we will take C2 as well.
If the number of tube rows are greater than 20 or equal to 20. Okay. If it is less than 20, then C2 will have a value. Okay, and you will get that value from table 7.6. Is it clear?
Yes. No, again.
You use this formula, also put C2 here, right? So C2 will be 1 if the NL is greater than 20. Okay, but if NL is less than 20, C2 will have a value which is not 1. But where will you get the value from? Table 7.6. Is it clear? Now?
20, then the S2 will not be 1.
C2.
C2, sorry.
Yeah. So the C2 values you will get from here then. For 1 tube row, 2 tube row, 3, 4, 5, 7, 10, 13, 16. If it is aligned, these values. If it is staggered, these values. Similarly, for the values of C1 and M, for the values of C1 and M, you will use this table 7.5. Okay? These is NL, number of tube rows.
Not set less than 20.
If it is less than 20.
About 17.
So it's 0.99, so consider it as 0.99
From 16 to 20.
to 20, consider it 0.99. Because at 20 it will become 1. Okay? Then in this table you will find out the value of C1 and M, and again you have to consider what is the maximum Reynolds number. So you will first find out the maximum Reynolds number, and then once you know the maximum Reynolds number, based on that you will determine whether it is aligned or staggered, and based on that you will determine what is the value of C1 and M. The whole course is like this. Now it is just empirical formulas and you should know how to use them.
Yeah. So we need to practice.
You need to practice.
more.
Okay? Anybody has any questions so far?
No.
For C2, we use after 20 tubes.
If it is less than 20, then use C2. If it is greater than 20, C2 is 1.
There is example.
Yeah.
Yeah.
See, show them.
Yeah.
لا
Now, it's written here that you will find out the Reynolds number max. So Reynolds number is basically what? Reynolds number is VD upon mu, right? So if it is Reynolds number max, so it will be Reynolds number max if we know what is the maximum velocity, right? So it will be Reynolds number max if we know what is the maximum velocity. Now what is the maximum velocity? For maximum velocity we have two formulas. Depends upon the case, whether it is aligned case, whether it is a staggered case. If it is aligned case, the formula for maximum velocity is this. Very simple. If it is aligned, the formula for maximum velocity is St upon St minus d. D is the diameter of the tubes. If it is aligned, multiply by V. V is the velocity, inlet velocity. Actually the thing is that the inlet velocity will change once it passes through the tubes, because you see the tubes are occupying some space, so it will so the velocity will increase, then decrease, then increase, then decrease. So velocity will keep on changing as it passes through the tube bank. Okay. So St is the transverse pitch. Remember the transverse pitch?
The aligned one.
Yes. St is the transverse pitch. D is the diameter. V is the inlet velocity. V is the inlet velocity. So this will be V max. Based on V max, you will find out what is Reynolds max. Based on Reynolds max, you will find out the constants. Is it clear?
There is another Vmax.
Another Vmax, because this is for the case of aligned. Right? Now come over to the case of staggered case. If it is the staggered case, you have two formulas. If it is the staggered case, you have two formulas, because you will first see this condition. If SD is less than this, then use this formula. Otherwise, use the same formula for the aligned one. Focus here. For the aligned case, Vmax, this formula. For the staggered case, there are two formulas. but based which one you have to use depends upon this condition. If this condition is satisfied, that means SD is less than ST plus D upon 2, okay, then you use this formula. If not, go back to the aligned case formula. Use the aligned case formula for the staggered as well.
The second condition?
One more time, please.
If this condition is satisfied,
How?
so you know what is the value of SL, you know what is the value of ST, you're going to substitute the values, you're going to substitute the value here, ST, D, and see if this thing is less than this or not. If it is satisfied, then use this formula.
Okay.
It's not used.
If not satisfied, use this one,
Even though it is.
even though it is staggered. Okay?
That means I have to do this form.
Yeah, for the staggered case. For the staggered case, first you need to see the condition. For the aligned case, no issue. Directly use this one. You understand this thing or not?
Yes,
So
I
far.
understand.
Now, if you want to find out, because what we are doing, we want to find out the heat transfer coefficient H, right? We want to find the heat transfer coefficient H across these bank of tubes when the flow is external. Okay? So basically, if we know H, you can find what is Q. Q is equals to H A delta T. Right? Q is equals to H A delta T. Now the issue is that what delta T will we be using? What do you think this delta T is? Ts minus T infinity. Perfect. Ts minus T infinity. But do you think the T infinity is same?
No.
T infinity is changing from rows to rows.
Yes.
Right? So at the inlet I have a different T infinity. At an outlet I have a different T infinity.
The average T infinity.
No, we are not going to use the average T infinity. What we are going to use is something you are going to use a lot in this course. And also in the fluid mechanics, I don't know about in the fluid mechanics we use much. But anyways, so this will use, this you are going to use this a lot in this course. From this chapter onward until chapter number 11, 12, you will be using it, right? And this is known as log mean temperature difference. Log mean delta T. Okay, that's why it's written as delta T LM. LM means log mean. Okay, and it has a formula. And what formula is that? Delta T LM is equals to delta T outlet minus delta T inlet upon ln delta T outlet upon delta T inlet. So delta T outlet is what? At the outlet, what is T infinity minus Ts?
T infinity minus Ts.
Right? But at the outlet,
I think you have to show me.
it doesn't matter. Even if you change it, so this will become negative, change it this one also, negative negative will cancel. So this is also okay, and delta T inlet minus delta T outlet over ln delta T inlet upon delta T outlet. Both are same. Is clear?
How?
Sorry?
How?
How they are same? So if you take it like this, if you do like this, it will become with a negative sign, right?
Yes.
This thing is equals to this thing with a negative sign, and this thing also equals to this thing with a negative sign. So this will become power here, and the power goes flips. Is it clear? So is it clear now? So you can use either this one or that one. Both is okay. Okay. So we have this. So delta T naught or delta Ti is what? At the inlet temperature difference, T infinity minus Ts. okay, and delta T naught will be T infinity minus Ts at the exit, okay. Obviously you have to remember that are you going to do Ts minus T infinity or T infinity minus Ts, depends upon if it is being heated or it is being cooled. So if it is being cooled, then the infinity temperature is higher, tube temperature is low, right? So let's say if the tube is cooler than the outside, okay, so you do T infinity minus Ts. If the tube is hot and the air is cold, so that's Ts minus T infinity you're going to do. So here we put here assuming that the tubes are hot and the air is cold, so we put here Ts minus Ti minus Ts minus T naught, okay. Consider this formula, okay, divide by ln Ts minus Ti upon Ts minus T naught. But remember one thing, if you are putting T naught here first, Ti here later, then T naught should be above, Ti should be below. If you are putting Ti up, T naught later, then Ti should be up, T naught should be below. This sequence should be like this. So both formulas are correct. Okay. But if you do like this, that you say delta T naught minus delta Ti upon delta Ti minus divided by delta T naught, this is wrong. Is it clear? So this is the delta T, log mean temperature difference, that we will be using. Is it clear? This is the log mean temperature difference that we will be using. Now in most of the cases, or in many cases, we know what is the inlet temperature, but we don't know what is the outlet temperature. Okay, we know what is the mean stream inlet temperature when the flow is entering into the tube bank, across the tube bank, but we don't know that when it has passed through the through the tube bank at the outlet, what is the temperature. If this is the case, then you need to find out first what is T naught, because until unless you don't know what is outlet temperature, you cannot find delta TLM. So in this case you have to use this formula. This formula is another formula just to find T naught, because if you don't know T naught, you cannot find delta TLM. You cannot find log mean temperature difference if you don't know what is T naught. And in most of the cases you have this condition, that you know what is the inlet, but you don't know after passing the tube how much is the temperature. Okay, so this is what Ts minus T naught upon Ts minus Ti equals to exponential negative pi d is the diameter, n is what? N is the total number of tubes, not just in a row, total number of tubes. Okay, multiply by h bar divided by rho v. V is the velocity, the inlet velocity. Nt, number of tubes in a row. Okay, Nt is number of tubes in each row. Okay, St is the transverse pitch, multiply by Cp, specific heat. Okay, so you use this formula to find out what is T naught. We are not going to go into how this formula is derived, just use the formula directly.
N is the total number of tubes.
N is the total number of tubes.
NT is
N is the number of tubes in a row.
NT.
NT, number of tubes in a row is written. I don't have any issue even if you put this description in the formula sheet. What is NT, what is N, I don't have any issue. My only concern is that you know how to use them, that's it. My only concern is that you know how to use them. Okay. Is it clear so far? Yes. So then it will become what? Now you have Q equals to HA delta T, right? Delta T LM. So if you know what is the log mean temperature difference, if you know what is H, you can find what is Q. What will be A?
Surface of the tubes.
Of the tubes.
Total tubes.
Total tubes. Okay. So what will be the surface area of one tube?
By D.
Pi D. Exactly. So if there are n number of tubes,
By EL.
pi dl, exactly. Sorry. So surface area of one tube will be pi dl.
N by DL.
So it will be n pi dl. So
There is no. There is no.
there is n here.
Where is L?
So that's why it is q dash
Over length.
over length. So you see here, heat transfer rate per unit length of the tubes. It's good, it's good. When you are active, I feel happy that I'm not talking to the walls.
Okay.
So far good?
Yes.
Any question? Because now we are going to solve a problem related to it.
Now, to get delta T, I need T naught,
If T naught you don't know, then you use this formula to find T naught.
then substitute in log, then use.
Exactly. So it's a lengthy problem actually.
Yes.
Can give us delta T.
Doctor, just write the formula here, because this three formulas, and then solve the.
It will take me time to write formulas. It's better to switch back to it. Okay, another very important parameter, another very important parameter is, look, whenever you have a flow which is passing through the tube banks, so automatically there will be a pressure drop. Okay, and this pressure drop is expensive. Why it's expensive? Because you make the air to flow by using a fan or a pump, which is not free, and it is using electricity. Okay, so how big it should be your fan depends upon how much will be the pressure drop in your heat exchanger. You want the air or whatever the fluid to pass through the tubes. If they are not going to pass through the tubes, there will be no heat transfer. But for making them pass through the tubes, you need to install a fan or something which will be using electricity, and that will cost you money. So it's a very, it is one of the most concerned things for the engineers is that to know that what is the pressure drop across the heat exchanger. If the pressure drop is high, so the operating cost will be high. And you know, everything in the end runs down to the economics. Okay, so is it feasible? Should I buy this heat exchanger? Should I install it? How much will be the cost? So the cost parameter is very strongly dependent upon how much is the pressure drop across the bank of the tubes across this heat exchanger. So this is a very fundamental thing for the engineers. Okay, so that's why we have this parameter delta P. How much is the pressure drop across these banks of the tubes? Okay, so it is given by the formula delta P equals to NL. Okay, NL, this is not multiply,
X.
this is X. This is not multiply, this is X. Rho V max square upon 2 multiplied by F.
What is F?
Now F and X are the two parameters which you are going to get from the chart. There is a chart here on the next pages. Okay, so the friction factor F and the correction factor X are plotted in the figures 7.14, 7.15. Okay, and that's it. This is a figure for the aligned case. If you have an aligned case, then you use this figure to determine what is the friction factor F, what is the F, this is not the friction factor, sorry, what is F and what is X. So for that, you need to know what is the Reynolds number, maximum Reynolds number, which you would have already calculated. Okay, and then once you know the maximum Reynolds number, then you need to know what is PL. Now what is PL and PT? PL and PT. So PL and PT are basically this. PL is SL divided by D, PT is ST divided by D. Okay? So if you know what is PL and PT, okay, so here for the staggered case, for the aligned case, you just need PL to find F. So you need Reynolds number. Let's say the Reynolds number is 1000 and the PL value is 1.5. So you come to here to the PL 1.5, and at 1.5 you see, check what is the value of F. Is clear? Similarly, you calculate this term here, PT by -1 divided by PL -1. Whatever the value is, you will come here, come to the point where what is the Reynolds number maximum, and then find out what will be your value of X.
It's a small drop.
It's a small graph. So approximation is good enough, if it is a good approximation. Now, do you know how to read a log table, a log chart?
A what?
A log chart.
Like this.
Like this. So here these values, they are given in the logarithmic term. Okay. So this is 10 to the power 1 means 10. This is 10 to the power 2
100.
means 100.
1000.
Okay. If I ask you where is 500, can you tell me?
Yes. There.
Between 10 to the power 2 and 10 to the power 3.
Where will be 500? Okay, so tell me where is 50. 10 to the power.
Not one.
50. This is 10.
This is 10.
Yes.
This is 100.
And this is 50.
50 years.
And this is 50.
Wrong.
Wrong?
That's why, because you don't know how to read a log table.
By the lines.
In the log table, the thing is that in the log table, it is not linearly placed. So this is, okay, how many points are here? How many lines you see here? 1, 2, 3, 4, 5. Right? So every line means 2 step. Right? 2 step. So this is basically 1 into 10 to the power 1. Then this is 2 into 10 to the power 1. Then 4 into 10 to the power 1. 6 into 10 to the power 1. 8 into 10 to the power 1. 10 into 10 to the power 1, which is 10 to the power 2. Okay, so this is 20. So that was 10. This is 20. This is 40. This is 60. So 50 will be between 40 and 60. You get it? Do you get it or not? This is how you read a log table. Don't read the log table in the standard linear way. This is not a linear one. This is a log table. Okay? Okay, so tell me 1000
Why there is line of mine?
tell me where is 2000? 2000.
The first line after 10 to the power 3.
Hmm?
First line after 10 to the power 3.
Exactly. So 10 to the power 3 is 1000. That means 1 into 10 to the power 3. So this will be 2000.
Then 4, 6.
Then 4, 6, 8, 10 into 10 to the power 3 is 10 to the power 4. This is not heat and mass transfer. This is mathematics.
Which
Regular calculus, I think. Calculus. You never.
maybe it's easy.
No, not statistics. You did not study the log table you've ever before?
No.
Okay.
So
Maybe in fluid.
why there is the space?
Huh?
Long space and small space.
Yeah, that's the thing in the log table. In the log table, everything is written in the power of 10. So that's 10 to the power 1, that's 10 to the power 2, that's 10 to the power 3, that's 10 to the power 4. So the difference between 1 to 2 is 100, 90. 10 to 100. What's the difference? 90. Then from here to here, it's 10 power 2 to 10 power 3. 100 to 1000, 900. That's the difference. So initial difference 90. This difference is 900. This difference is 9000. Okay. So we have cases where log table is very good, and not when you have cases when there is not much variation with time, and the variation becomes small at larger values, then you have to use the log table. Because if you do not use the log table, these curves would turn out to be like a straight line throughout big. Okay. Do you understand how to read a log table? Okay.
So what about the y-axis?
Do you think the y-axis is a log, also log, or do you think it is linear?
The same.
It's also log. If it is linear, then the distance between point 1 to point 2 should be same between point 2 to point 3. But if you see here, point 1, point 2, point 4, point 6, this is point 8, then 1. Then 2, 4, 6, this is 8, then 10. So this is a log chart. This is a log chart. And when you have to read values from the log chart, you must be sure that you are reading the right values. So it's not linear. Okay. Suppose the value comes at 1000 for 1.5. What will be the value here?
0.3.
So it will be approximately 0.3. If you write 0.3, it's good enough for me. Okay. But here the good thing is that the values are written here like this. If they were not written here like this, if it was written 10 power minus 1 and this 10 power 1, sorry, 10 power 0, then this 10 power 1, and the values were not written in between, then you might get a wrong value considering it to be linear.
Yes.
Okay. So it's important that you know how to read the log chart, and I will make sure that you know how to read a log chart. Keep that in mind.
We have to read the formula sheet.
Yes, this will be in the formula sheet. Oh, this is- So this is for the case of aligned. For the case of staggered, you have this. It's a similar kind of sheet, but this is for the case of staggered. That was for the case of aligned. Okay. Now in the staggered case, if you see here,
Minus 1. Yes.
10 power minus 1, 10 power 0, 10 power 1, nothing written in between. But you have to guess the right value.
You have to do everything.
Huh?
You have to do everything.
Of course.
Because we are engineers.
Huh?
We have technicians to do that for us. Right?
Only 10 minutes. I think only 10 minutes.
No. Inshallah, we'll finish this chapter. That's
It will
it.
take 3 hours next Tuesday.
Okay. Let's come to this numerical, and after this numerical, our external flows are finished. Okay. So all formulas that you studied before, now we are going to apply. Pressurized water is often available at elevated temperatures and may be used for space heating or industrial process applications. In such cases, it is customary to use a tube bundle in which the water is passed through the tubes. So what is passed through the tubes? Water. Water is passed through the tubes, while air is passed in cross flow. So we have in the cross flow condition, we have the air. Okay. In cross flow over the tubes, consider a staggered arrangement for which the tube outside diameter, so D is given, this is D, and the longitudinal and transverse pitches, SL is given, ST is given. Okay. There are 7 rows of tubes in the airflow direction. So this is what? This is NL, number of tube rows, and 8 tubes per row. So this will be what? NT, number of tubes per row. NL is number of tube rows. It's clear? Anything not clear? Ask.
The vertical is row or column?
Here there is no column. Just consider rows and then number of tubes in a row. Rows, number of tubes in a rows. Normally in mathematics we consider vertical as column. Here they are putting it as rows. So rows and number of tubes in a row. Okay. So number of rows are 7. Number of tubes in a row are 8. Okay. Under typical operating conditions, the cylinder surface temperature is 70 degrees centigrade, while the air upstream temperature, air inlet temperature, upstream comes first. Air upstream temperature and velocity are, so we know what is the velocity, we know what is the T infinity inlet. Okay, are 6 meter per second. Determine the air side convection coefficient, H. Air side convection coefficient. Air side is the outside. Water side would be inside the tubes. That's chapter 8. Internal flows. This is external flow. Right? So determine the air side convection coefficient and the rate of heat transfer from the tube bundle, Q. What is the air side pressure drop? Delta P.
We have 3 things to determine.
You have to determine everything. But the important thing is that, do you understand what is given? Do you understand now how to proceed into the problem? So for finding H, you need to know what? You need to know the Nusselt number. But for finding Nusselt number, you need to first know what is the Reynolds number. But finding the Reynolds number, you should first know what is the velocity maximum. But this is the staggered arrangement. So first you will check the condition with which formula will be used for the finding the maximum velocity. So everything is like given, but you should know how to use it. That's it. And this whole course is about it, like this.
It can come in the major.
Can come?
It's 2 hours to solve.
No, it's really not that much big to solve.
Yes, sir. In the question, you must give us the schematic diagram. It's very important.
We'll see. We'll see. Okay. First of all, do you understand the problem statement or not?
Yes.
Yes.
Okay. So now let's come over to the solution. Okay. Now in this case, you know what is the inlet temperature, but do we know what is the outlet temperature?
So we have to find it.
So we don't know what is the outlet temperature. Okay. Now the question is that at what temperature would we find out the properties?
The log.
The thing is that you remember we said that we will take the mean temperature inlet and outlet, but we don't know the outlet temperature.
So we find the outlet.
We only know the surface temperature and we know the inlet temperature. So we will take the properties at the inlet temperature right now. Okay, and the mean film temperature. So mean film will be what? It will be the surface temperature and the inlet temperature, average of the two, because these are the two temperatures we know right now. Okay, we don't know the outlet temperature. Actually, in the problems of heat and mass transfer, this thing happens a lot. And when you come over to the internal flows, it will happen even more a lot. That you need to find out the properties at the average, but most of the time you don't know the average, because you know only one side temperature, other side you don't know. So what you do is that first you take the first one side temperature and get all the properties from that and solve the problem using those properties. And then once you solve the problem totally, you will find out the outlet temperature and check whether that outlet temperature is how far off from the inlet. If there is a big difference, then you have to resolve the problem again. Now considering if there is a big difference between inlet and outlet, then you have to resolve the problem again using the mean temperature now. and then you will have again a little difference. Then you resolve it again.
This is the third time we saw.
Then you keep on solving until a time reaches when the outlet temperature remains the same as whatever you got.
But why? I'm not the scientist.
That's the thing. You're not going to do like this. But you're not going to do like this. But this is kind of an iterative problem. Okay, and this happens. That's why we have the softwares, and we make the problem put into the software, so that every time it solve it, find the other temperature, and then we take the mean, then solve it again, find the other temperature, then we take the mean. A time will reach when the other temperature is the same as what mean you are taking based on that. So at that time your solution has converged, and this is the correct solution. But this is an iterative procedure. You have to repeat it again and again and again. And normally in these cases, for you in the exams, even if this is the condition, you will not be asked to repeat it. You are just asked to write it one time, and in the end you might be asked, okay, tell, do you think repetition is required or not?
Nice, like this.
Okay. So anyways, we will come to that. So now we use the Nusselt number is equals to C2 into C1 Reynolds max Prandtl number over Prandtl S. This Prandtl S should be taken at surface temperature. Okay. So now in order to find these values, first we need to know what is the Reynolds max. Okay. So Reynolds max for finding this is the staggered arrangement case. So Reynolds max is basically V max D upon mu. But first we need to know what is V max. Since this is a staggered arrangement case, we need to see which formula we have to use for finding V max. Once we substitute the values of SL and ST, which is given in the problem, we will find SD as 37.7 millimeter. Okay, and SD plus T upon 2, so this thing is greater than that. So that means the condition is not satisfied.
So,
Since the condition is not satisfied, we will use the formula for the aligned case. Otherwise, we use the other formula. So that's why here we use the formula for Vmax for the aligned case. Substitute all the values, you will get what is Vmax. Now once you know what is Vmax, just substitute the values, you will get what is the Reynolds max. Once you know what is the Reynolds max, now come back here. Now you know what is the Reynolds max, you know what is the Prandtl, you know all these properties. You need to know the power m and C1.
Table 7.5.
And also you need to find C2. So how many rows you have? 7. So it is less than 20. So that means there will be a value of C2 here. Okay. So if you go back. Okay. So for 7 rows and for the staggered case,
0.595.
your C2 value will be this, right? Now, what was your Reynolds number? Reynolds max came out to be 13943, right? So I write here 13943. So come back here. 13943, in which range it will come? 10 into 10 to the power 2? No. 10 power 2 to 10 power 3? No. 10 power 3 to 2 into 10 power 5?
Yes.
Yes. Within this range it will come. But within this range, I have one case for the aligned, but is our case aligned? No. So this is not the case. So we will consider staggered case. But for staggered we have two cases. Either ST by SL less than 2 or ST by SL greater than 2. But we know what is ST and we know what is SL. Substitute the values and find out what is ST by SL. So in this case, in our case, ST by SL is 0.91. So it's less than 2. Okay. So come back here. So it is less than 2. That means this is the case that we will be using. Right? So for this is the case, C1 will be this thing and M will be this. Get it? So now we know the value of C1, we know the value of M, we know the value of C2. Now we know all the values to find out the Nusselt number. Right? So go back. So now we just substitute the values. You get C2, M, C1. Substitute the values, you will get what is Nusselt number. Once you know Nusselt number, substitute the values to get H. Now we know H now. This is the thing we know. We need to find out Q. For finding out Q, we need to find out what is delta TLM. For finding delta TLM, we need to know what is T naught. So for finding T naught, we will use that formula. It's the same formula which was given. Okay? All other parameters known here. All other parameters known here. Except T naught. So we'll find out what is T naught, or just directly put Ts minus T naught because this thing is needed here. Okay, and also here. Okay. So substitute in the values to find out what is delta TLM. Once you know delta TLM, substitute in this equation to find out what is Q dash. Okay.
We found Q.
So we find Q. Now the only thing left is the pressure drop.
Delta P.
Delta P. Okay. So for finding pressure drop, it is this formula, right? But in this case, you need to find out the value of F and X from the chart for the staggered arrangement. Okay. So Reynolds max is known, and PT is ST by D, which is 1.91. PL is SL by D, which is 2.09. So PT by PL will be 0.91.
Use these values in the chart.
Use these values in the chart. Okay. So Reynolds number about 14,000, 13,943, right? About 14,000. So 14,000. So let's go back into the chart. So this is for the staggered arrangement. So 14,000 will be where?
Yeah.
So tell me where will be 14,000?
14,000.
Second line.
Between the second line and third line. After 10 to what?
No. Here.
Between the first and the second.
Here. Somewhere here.
لا يا بابا
لا
14,000
بعد
14
10 3.
عند ايوه نفس المكان عند 10 بس 3
هنا?
ايوه.
Wait.
يقول لك لا.
He's correct.
No. This from 1,000.
He's correct.
This one from 1,000 to 10,000.
10,000. Yes.
Second line after M to power 4.
So it should be after 10 to the power 4, right? So this is 1 into 10 to the power 4, that is 10,000. This is 2 into 10 to the power 4, which is 20,000. And your value is 14, between 10 and 20.
Of the middle.
So even if you put it in the middle, I will not put it wrong. Okay? If you put it in the middle, but where you have to stop, you need to know what is the PT value, stop there, then come here and find out the value. This log scale, since this is something new for you, so remember, this is important.
We have to know this.
You should know this. Where is? Oh.
So we finish.
End of the lecture.
No.
Yes. This
Skip the lecture.
يعني راح كل الحفظ
So now you just substitute the values. In the end, you will find out delta P, and this delta P is in the unit bar. Why is it in unit bar?
Atmosphere, surveyor, something like that.
Because I'm concerned about the units a lot. So this delta P is in bar.
So if I want it, you convert it. You just convert it.
So I just converted it. It was actually in Pascal.
I will leave it.
You can leave it in Pascal. It's up to you. But if I write it that find out delta P in bars, then you have to find in bar.
and then you have to give the coefficient of conversion.
Get idea.
Do you know what is the conversion coefficient from bar to a Pascal? 10 power 5.
Chapter 1.
So alhamdulillah, external flows are done here.
Alhamdulillah. And we are done also.
Okay.
And we are going to start from chapter number 8, internal flows, inshallah, next class. And next week, instead of lab, we will have a class. So we will inshallah finish chapter number 8 and chapter number 9 next week.
We have to slow down.